Greetings and welcome to the 18th clinic in linear algebra. Today's clinic is going to focus on problems about linear transformations, specifically the definition of a linear transformation. So what we'll be doing mostly is just showing that some given mappings are linear transformations. Okay, and I think we do look at a property. Okay, so let's get started, right? So I want to show that mapping f from R2 onto R2, defined by f of xy equals x plus y x, is a linear transformation. Okay, so we have to show that it satisfies the two properties of linear transformations, specifically that f of u plus v is f of u plus f of v, right? And then f of k times v is equal to k times f of v. So let's say that xy and x prime, y prime are vectors in R2. And of course, k is some real number, okay? So what we're looking at is f of xy plus x prime, y prime. Well, by definition, this is f of x plus x prime, y plus y prime. Now, by the definition of the transformation, this will give us x plus x prime plus y prime, and then x plus x prime. But since x prime, y, and y prime are all real numbers, we can rearrange this however we want. So we can write this. And then say this is clearly the sum of two vectors, x plus y, x, and x prime plus y prime, x prime, which by definition would be f of xy plus f of x prime, y prime, which is what we wanted. Okay. Now, f of k times xy. Right, by definition of multiplication, this is kx, f of kx, ky, which by definition of f, kx plus ky, kx. But from the first component, we can factor out a k, right, which allows us, by definition of multiplication, to factor it out of the vector. But then that vector is just f of xy. Okay. So then this mapping is a linear transformation. So now I want to show that this mapping F from R3 into R2 is a linear transformation. All right, so we're going to need a vector in R3. I'm sorry, two vectors in R3. And obviously a real number K. All right, so let's look at F of their sum. So by definition, of course, of addition, that's F of this. And now by definition of F. There's the first component and then the second component. Right, now we just have to simplify everything, okay? So in that first component, we can group the non-prime terms and the prime terms together. Right? In that second component, we can distribute and then group. Then, of course, we have the sum of two vectors. That first vector, by definition, is the transformation of x, y, z. Right? And that second vector, by definition, is the transformation of x prime, y prime, z prime. Okay, now we just need to look at the transformation of k times x, y, z. Right, by definition of scalar multiplication, this is the transformation of kx, ky, kz. And then by definition of f, kx plus ky plus kz, 2kx minus 3ky plus 4kz, which we're of course allowed to factor out the k. Right? Which of course that is the definition of the transformation x, y, z. Conditions are satisfied. And this mapping from R3 onto R2 defines a linear transformation. Right, so let M be an arbitrary but fixed matrix in M22. Define the transformation from M22 into M22 by this setting. F of A equals AM plus MA. We want to show that this defines a linear transformation. Right? So what we do is we say let M in M22 be fixed, and now we need two matrices in M22 and a scalar R, or a scalar K, right? If we look at F of A plus B, by definition of F, this will be A plus B times M plus M times A plus B. All right. Now, since A and B are 2 by 2 matrices, their sum is a 2 by 2 matrix. So we have a 2 by 2 times a 2 by 2, that's defined. We have a 2 by 2 times a 2 by 2, that's defined. Both of these products will be 2 by 2 matrices, right? So we have a 2 by 2 plus a 2 by 2, which is 2 by 2. It is defined. So we are allowed to write this, right, by definition of matrix multiplication. Right, so we have the sum of a bunch of 2 by 2 matrices, right? Well, we know it's associative, that addition is associative and commutative. So we can write this. But that's the definition of F of A, right? Plus F of B. Now look at K times A, right? By definition, this will be K times A M plus M times K times A. Right, well, how we write the K, where we write the K doesn't matter. So what we can do is factor out a K, and we'll be left with AM plus MA. Right, and the reason for that is because, right, this here is the same as this. Right, and then this is that, right? Which is the definition of K times F of A, right? So therefore, our transformation, or our mapping from M22 into M22 defines a linear transformation. So let V and U be vector spaces. Suppose that the set V1, V2, Vn defines a basis of V, and let's suppose that U1, U2 up through Un are any vectors in U. We want to prove that there exists a unique linear transformation, f from V into U, such that f of V1 equals U1, f of V2 equals U2, right? So on and so forth. Right, so proof. Let V be a vector in V now, since this set defines a basis for V, we know that there exists unique constants C1, C2 through Cn, such that V equals C1 times U1 plus, I'm sorry, C1 times V1 plus C2 times V2 plus so on and so forth. Now what we do is say define a mapping from V into U as f of V equals C1 U1 plus C2 U2 plus so on and so forth. Notice that f of V sub I would equal 0 U1 plus 0 U2 plus so on and so forth plus C sub I U sub I. I'm sorry, plus U sub I plus so on and so forth, right, plus 0 U sub n, which is just U sub I. What we do is we say, okay, let V and V prime be vectors in the vector space V and define some constant K. Then what we have, right, is V is equal to C1 V1 plus so on and so forth. I'm going to shorthand it at this point. And V prime, let's call it C1 prime V1 prime, or no, just V1 rather. All right, then plus Cn prime Vn. So this would mean that if we take the sum of these, right, we would get C1 plus C1 prime V1, right, plus so on and so forth, and then Cn plus Cn prime times Vn. So f of V plus V prime, C1 plus C1 prime U1, right, and then plus Cn prime Un, which we're allowed to write as C1 plus so on and so forth plus Cn Un plus C1 prime plus so on and so forth. I screwed that up. It'd be C1 U1 plus so on and so forth plus CN UN, and then plus C1 prime U1 plus so on and so forth plus Cn prime UN. But this is the definition of f of v plus f of v prime. If we look at k times v, right, this will be ka1v1 plus so on and so forth. These are supposed to be c's. Of course, it erases everything, so whatever. Right, so we look now at f of kv. And so that's this, which we're allowed to factor k out of. Which of course is just k times f of v. So this mapping that we just defined defines a linear transformation. Now we just need to prove that it's unique. So finally, suppose we have a mapping G from V into U that is a linear transformation. Such that G of V sub I equals U sub I, right? Just as we've done in F. So let, again, V equals C1 V1 plus so on and so forth. Right. Then if we take a look at G of V, right, what we get is this. But since G is a linear transformation, we can write this. This equals C1 U1, right, plus so on and so forth. But this was f of v. So what this shows is that G of v equals f of v for every G in V, and hence f is unique, which is what we wanted. So in this one, we're given a linear transformation from R2 into R2, for which f of 1, 2 is equal to 2, 3, and f of 0, 1 is equal to 1, 4. We want to show that 1, 2, 0, 1 defines a basis for R2, and then find a formula for f. Well, proving it's a basis is simple enough. We've done that plenty of times. So for augmented matrix, we're going to be left with this. So this shows this set spans R2. Right? And then by setting A equal to B equal to 0, this also shows the set is linearly independent. Therefore, this set 1, 2, 0, 1 defines, defines a basis or forms a basis of R2. Now we just want a formula for our transformation. Now from above, we have that any arbitrarily chosen 2 vector, AB, is equal to A times 1, 2, plus negative 2A plus B times 0, 1. So therefore, F of AB be equal to A times F of 1, 2, plus negative 2A plus B times F of 0, 1. Applying the transformation. Right, so we're told that F of 1, 2 is 2, 3. We're told that F of 0, 1 is 1, 4. Right, so what we can do now is combine these. So we get 2A minus 2A plus B, right? And then we get 3A minus 8A plus 4B, which is equal to B negative 5A plus 4B. And so there is our F, right? So therefore, our mapping F from R2 into R2 is defined as, what I can do now is just write as F of xy, doesn't matter. F of xy equals y negative 5x plus 4y. And that concludes today's clinic. Thank you, everyone, for attending. Thank you all for watching. See everyone again next time.